All right, so this is going to be a review for the physical science final exam. Okay, so first of all, let's talk about matter. All right, matter is anything that has mass and volume. Okay, and then matter can be divided into two categories. We have pure substances and mixtures. Okay, now the pure substances can either have only one kind of atom or it can have more than one, two or more kinds of atoms chemically, and that's a key word here, chemically bonded. All right, so if there's only one kind of atom in the matter, we call that an element. Okay, if there's more than one kind and they're chemically bonded, then we call that a compound. And the smallest part of an element that is an element is, of course, an atom. And the smallest part of a compound that is a compound is a molecule. Okay? Now, for mixtures, we have two kinds, and they're separated based on whether or not they scatter light or settle. All right? So a solution never settles or separates, never separates. Think of tap water. Okay, it's a mixture. It's got ammonia added to it, it's got chlorine added to it, it's got air dissolved in it, it's got, of course, water molecules. So it is a mixture, but it never separates. You never get a glass of water like, oh man, all the carbon dioxide settled to the bottom. That never happens. It never separates. And the particles in the solution are so small, they do not scatter light. Okay? And then over on the other side, all right, so another type of mixture on this branch is something called a colloid. Now, a colloid never settles or separates. Think about milk. Okay, now it does separate when it spoils, but that's a chemical reaction has happened at that point. When you just buy milk, homogeneous milk or homogenized milk, it doesn't settle or separate. Okay, but the particles in a colloid are big enough that they do scatter light. Okay, now here's the thing. So both of these are going to be the same throughout. If you have a beaker of tap water, okay, then the ions and stuff added to it to keep it clean and safe to drink, they're evenly spread out through the whole thing. If you have a glass of, say, juice or like apple juice or milk or even Jello, right? It's going to be the same throughout. The particles are just going to be a little bigger, and they're going to they're big enough that light can bounce off of them. Okay, so these are both what we call homogeneous. They're homogeneous mixtures because they are the same throughout. If I take a sample up here or I take a sample here, it's going to be the same. Okay. Now, the other group of mixtures is what we call heterogeneous. All right, so let's review our root words. Gen means origin, homo means the same. So everything in here has the same origin. So it's the same throughout. Hetero means different. Okay, so with heterogeneous, think about muddy water, right? It may start off fairly homogeneous, but if you leave it over time, some of that stuff is going to settle to the bottom. Maybe still some stuff up here, but some of it's going to settle to the bottom. Okay, so heterogeneous, they do separate. Okay, and they do scatter light. All right, so there you go. Those are the categories of matter. All right, so examples of an element could be like gold, silver. Oops, no, this is silver. AU is gold. Na is sodium. Okay, there's 118 elements on the periodic table. There's 3 of them. Compounds could be things like NaCl or H2O. Okay, there's more than one kind of element and they're bonded together. Solutions are things like tap water, air, doesn't have to be a liquid. Okay, tap water, air, soda. Colloids are things like milk, Jello. That's all I can think of at the moment. Heterogeneous mixtures. Oh, like a latte would be a colloid because the milk doesn't settle to the bottom. Heterogeneous things are like oil and vinegar dressing. If you've ever had medicine where you had to shake the bottle before you take the medicine, all right, that was the suspension. Oh, I forgot. Yeah, these are called suspensions. All right, so you have solution, colloid, and suspension. Solutions and colloids are homogeneous. Suspensions are heterogeneous. Muddy water would be a suspension as well. All right, so that's matter. All right, let's talk about bonding for a second. Okay, there are 3 basic types of bonding. There's ionic, covalent, and metallic. All right, ionic bonds are going to be between a metal and a non-metal. Now, if you remember on the periodic table, here's a quick sketch of the periodic table. It's not very accurate, but work with me. All right, generally speaking, over here you have the metals. Hydrogen is a non-metal. And then over here you have that stair step. The stair step is the metalloids. And then over here you have the non-metals. All right, so an ionic bond is going to be between a metal and a non-metal. Covalent bonds are between 2 non-metals. All right, so 2 of these guys. And then a metallic bond is between a metal and another metal. Okay. Another difference is ionic bonds, the metal loses electrons and the non-metal gains electrons. So another way of saying that is they transfer electrons. Covalent bonds share electrons. And metallic bonds are similar to covalent bonds. You basically have, like, let's say this is a sodium nucleus and another sodium nucleus, and another sodium nucleus, and they're all sharing their electrons. So there's like this sea of electrons around all the metal nucleus, right? And so you have a sea of electrons. Okay. So if you were to look at the periodic table, let's draw another one on here. Right? And they gave you an element over here and an element over here, and to ask you, let's say X and Y. Okay, so X and Y, that's a metal and a non-metal, so that would be an ionic bond. If they gave you A and B, okay, A and B would be a what? Yep, it would be a metallic. And if they gave you Q and Y, that would be a what? That'd be a covalent. Okay? So you will have a periodic table. It will have the symbols and the names and the atomic numbers. It will not say metal or non-metal. You have to know where those things are. Okay? All right. Now let's talk formulas. So if you had, let's say, sodium and oxygen, and they're going to form a compound. Well, remember on the periodic table, everything in group 1 is a 1 plus. Everything in group 2 is 2 plus, and then 3 plus, 4 plus, 3 minus, 2 minus, 1 minus, and then 0. Okay? So here's a periodic table. Ignore this gap in the middle. This was on 2 separate pages, and I just put them together. So if we're looking at sodium, it's over here in group 1, okay? And oxygen is over here in group 16, right? There's oxygen. So oxygen is in the 2 minus, right? So that means, so oxygen wants to gain 2 electrons. Sodium is a 1 plus. It wants to lose 1 electron to become stable. All right, so what that means is I need 2 sodiums to give electrons to this oxygen to form a stable compound. And so what you're going to end up with is you're going to end up Na12, subscript 2 tells you how many atoms, O. Okay? I don't need to put a subscript there because if there's no subscript, it's understood to be 1. Okay? If you were doing a covalent bond, then it's a little bit different. We'll cross that road if we come to it. And this would be an ionic bond because you have a metal and a non-metal. If you had to name this, you would just say sodium, and then you take oxygen. It's oxygen. You drop the gen, and you add IDE. So this would be sodium oxide. All right. Now, going back to covalent bonding a little bit, let's say you had NH4Cl. All right. Now, chlorine, we can look at the periodic table, and we find out that that's a 1 minus. Now, NH4 is a polyatomic ion. The NH4 stays together in chemical reactions, and it is a 1 minus. Okay? So, I'm sorry, that's a 1 plus. So even though this is 2 nonmetals, it takes the place of a metal because it's positive. So this would be an ionic bond. Okay? If we look at K2SO4, okay, potassium, we look at the periodic table, it's a 1 plus. It's in group 1. SO4 is a polyatomic ion, which is 2 minus. Okay? Now, again, we have a positive and a negative. So this polyatomic ion is taking the place of the nonmetal. This is an ionic bond. All right. If we have C6H12O6, okay, then we have a nonmetal, nonmetal, and a nonmetal. So this is most likely a covalent compound. Okay. So if you have a positive and a negative, it's probably ionic. If you have something like KCl, you have a metal and a nonmetal, that is definitely ionic. Okay? If you have a positive and a negative, or a positive and a negative polyatomic ion, or a positive polyatomic ion and a negative, that's ionic. If you have all nonmetals, it's covalent. Okay? All right, so when we talk about radiation, okay, you have an element where the nucleus is unstable and it breaks down. That's what radioactivity is. And when they do that, there's three kinds of radiation. There's what we call alpha decay, there's beta decay, and then there's gamma decay. Gamma radiation will not turn you into the Hulk. It will give you cancer and or kill you. All right, alpha decay is going to be 2 protons and 2 neutrons. Okay? And then a beta decay is an electron. Okay? And then gamma radiation is an electromagnetic wave. Okay? And since this is 2 protons and 2 nucleus, this is basically a helium nucleus. Okay? All right. All right. And so gamma radiation will penetrate the most. You would need a lot of protection, like really thick lead, to protect yourself from gamma radiation because it's just a wave. We are protected on Earth by the Earth's magnetic field. Beta decay are electrons. They're very small, so you need more protection from them. And then alpha decay doesn't penetrate that much. You can stop them with like a few sheets of paper usually, and because they're much larger. Okay, so this is the most penetrating because it's electromagnetic. This is second because it's small, very small. And this is third because it is the largest. Okay. Moving on. All right. So let's say you have a graph. The graph looks like this. And you have temperature on this side and it's going up, and you have time on this side and it's going that way. It's going up that way. And you look at the graph and it looks like this. Okay. And so what we can tell here, this would be a cooling curve. I know it's a cooling curve because the temperature is going down. If it was like this, it would be a heating curve because the temperature is going up. All right. Now, either way, in this scenario, in the cooling curve, you are starting with the gas. And at this point, if the temperature is going down, you are condensing. And then you're a liquid. And if the graph kept going, it would flatten out. And then it would go down again. This would be freezing. and as the temperature goes down, and this would be a solid. Okay. On a heating curve, it's the same thing, just opposite. So you'd have a solid here, and as temperature goes up, then temperature is going to stay the same while it melts, and then temperature is going to go up again because now it's a liquid, and then temperature is going to stop going up because, and then it's going to vaporize or become a gas, and then it's going to be a gas. So what's happening on the slanty bits is the molecules are moving faster, right? That the temperature, the energy that's being added is causing the molecules to move faster, and that increases temperature, right? On the flat bits, the plateaus, instead of the molecules moving faster, they start moving farther apart. And that's what causes them to melt, is that moving apart. So temperature, the energy, instead of making the molecules move faster, makes them move apart. That's why the temperature stops going up. Okay? Or in this cooling curve, the temperature stops going down. Okay? So if the question, it's on a heating curve, it's going to be solid, liquid, gas. On a cooling curve, it's going to be gas, liquid, solid. And I would expect a question about these flat bits. And then the answer is going to be, well, it could be, for example, here, that the gas is becoming a liquid, but you might also say that the molecules are moving farther apart rather than moving faster. All right, the other thing to note here is that because this is a cooling curve and temperature is going down, all right, energy is being released. So like right here, energy is released. Okay, and then energy is being released here as it freezes. On the other hand, on the heating curve, in order to vaporize or to melt, heat has to be absorbed. Okay, so on the flat bits, there's a phase change. On a cooling curve, energy is being released. On a heating curve, energy is being absorbed, and the molecules are moving farther apart. They're moving faster on the slanty bits, or slower in this case, faster in this case, and they're moving closer together on the flat bits. On the heating curve, they're moving farther apart on the flat bits. All right. All right, now we haven't talked about electricity a whole lot, but you might see a question about it. So let's take a quick look here. All right, so this symbol means resistor. Now it could be a light bulb, or it could be something called a resistance. This symbol means battery or power source. And then, of course, the line is the wire connecting all of it together. Okay? And so then if we know that this is, say, 20 volts, that's the potential difference between the positive and the negative side of this battery. And then let's say this is 6.1 ohms of resistance, and well, let's just say 6 ohms, and let's say this is 5 ohms. Okay, now resistance is just that, is a resistance to the flow of electrons. So as the electrons go through here, they're going to have some resistance in the wire, and then they're going to have more resistance. And they have more resistance here because this is a higher resistance value. So this is more resistance than this one. And we also know this is since it's basically the electrons are going to go from A to B to C and back to A. A, B, C, 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 A. So this is what we call a series circuit. Now you could also have a circuit that was set up something like this. And so now the electrons are going to come out, and some of the electrons will go this way, and some of the electrons will go this way. And they'll go through and all the way through, and these electrons will go through and all the way back around. So this is what we call a parallel circuit. Okay. All right, now a question you might get asked about this is what would happen if you double the voltage? Well, the equation you need is that voltage is equal to I is the current, and R is the resistance. So voltage is just, it's like the steepness of a hill. It's how likely the electrons are to flow, right? Current is the actual flow of electrons. So it's not the voltage that kills you, it's the current. Okay? Hopefully you'll never be electrified or even shocked, but it's the current that gets you. So, and they might ask, like, what happens if we double the voltage? Well, since this is a series circuit, I can just add the resistances together and get a total resistance of 11 ohms. Okay? So then what I can do is I can, if I don't know the answer off the top of my head, I can just say 20 volts is equal to I times 11 ohms. Okay? And so then I'm going to divide both sides by 11, and I find out that it's like 1.8 equals I. And that's going to be in a unit called amps or amperes. All right. Now, if we double the voltage, then we're going to say 40 equals I times 11. We, again, divide both sides by 11, and this time we get 3.6 amps of current. So if you double the voltage in a series circuit, you get double the current. Okay? Parallel circuits are a little trickier. I don't think you'll have any questions about those, but if you do, I'll cover it in an upcoming video. All right, now a word about resistance, electrical resistance. All right, now remember we talked about how metal bonding. So you have, say, copper electron or copper nuclei. And then around these copper atoms is a sea of electrons, a sea of shared valence electrons. And because of that, new electrons, like from a battery or an outlet, they can flow through here fairly easily, right? And come out the other side. That's why we use copper in like all of our electronic wiring. Power cords, cell phone chargers, headphones, wired headphones, they have copper for the wires because it's really good at allowing electrons to flow through it. Okay, now if you have a large diameter wire, okay, then lots of electrons can flow through fairly easily. But if you take and you make that wire smaller, then fewer electrons are going to be able to flow through it. So this small wire will have more resistance than this larger wire. Okay? So that's why engineers know what size to make wires. And some things that have a small amount of current flowing through it, like say headphones, you can use very small wires. But other things like a washing machine or a dryer, they have much more current flowing through them. So they have to be thicker wires to handle that. Okay. All right. Now, an electromagnet. Basically, you have an iron core or something similar to iron, and you're going to wrap around that copper, and you're going to hook that copper to some kind of power source, possibly a battery. And as the electrons flow through this wire, they're going to induce a magnetic field around this iron core. So here's the magnetic field. Okay, and so now, as long as there's electrons flowing through that copper wire, you have an electromagnet. Okay, now if you want the magnet to be stronger, then you could increase the current, or you could increase the coils of wire. So if you had two electromagnets and one looked like this and the other one looked like this, this one has more coils, this will be a stronger magnet. Even with the same battery, you have a double A battery here and you have a double A battery here, this will still be a stronger magnet because it has more coils of wire. Alternatively, if you have two identical electromagnets, let's see if I can draw this kind of identical. If you hook up, let's say like a 9-volt battery here, okay, this will be the stronger battery because this is only 1.5 volts, okay? So this will be the stronger battery of these two identical batteries. But if you have more coils, you have a stronger electromagnet. One more on electricity, and then I'm going to stop this video and I'll do another one. So there are these things, and you may have heard people talk about them, like a blown transformer when we talk about power outages. Your laptop, like let's say this is your laptop, right? And you've got the cord that comes out, and then most laptops have a big block in the middle, and then you have the plug that you plug into the wall. This is a transformer, okay? Because the wall outlet is a higher voltage than what the laptop actually needs. So this is a step down transformer. It decreases the voltage. So a step down transformer decreases voltage. Okay. A step up transformer is what you have on the power lines. So like if you ever see, like here's the power lines and it runs through like this, and then you see like a big round thing on the side of it, that's the transformer. All right, step down transformer a step up transformer increases voltage. All right, and so what happens is you have, this is kind of like the electromagnets. So you have this is your iron core, but it's like a loop or a square. And on one side, you have lots of coils, all right? And so here you have the incoming power from whatever source, okay? And the power is going in and coming back out. And then over here, you have fewer coils, and it connects to wherever the power is going. This would be a step down transformer. So what happens is these coils, just like an electromagnet, induce an electric or a magnetic field in this iron core. But because this is a big loop, that magnetic field induces an electric current in this wire. So you have a higher voltage up here and a lower voltage over here. So this is a step down transformer. Now if you had it the other way and you had power coming in here and you had a few coils here, and you had lots of coils here, and the power going out, this would be a step up transformer. This is a step down transformer. So how does a step down transformer alter the amount of voltage from a power line? So a step down transformer has fewer coils on the secondary coil, and so it reduces the voltage by reducing the coils. A step up transformer increases the voltage by increasing the number of coils. Okay? All right, so that's a bunch of information for the exam. It's not all of it. We haven't even done forces in motion. But that is a good start, and I'll see you in the next video.